Welcome to Mr. Bixel's Tutorials. This is the lab prep for what is the best way to the top of the mountain. I want to first start off talking to you a little bit about some different roads. Right here, what you see is the North Yungas Road. That's in Bolivia. That's the Bolivia's road of death. That's the most dangerous road in the world, as you can see just by looking at it. You can see that the road is so narrow here that the trucks have to basically park and squeeze by one another. This truck is in a very narrow section, and if this wheel here goes off the edge there, it's all over. And you can see that you've got two tourists and you've got a tour bus here. And if this thing goes off the edge of the cliff, it's 9.8 meters per second squared all the way down. What you've got here is the Guiliang Tunnel Road. That's in the Taihang Mountains in China. There's a little village that was cut off from pretty much all of civilization, and the village elders decided they wanted to do something about it. So they sent 13 guys. They sold a bunch of goats, bought some hammers and some steel chisels, and cut a road through the side of the mountain. And the road's about a mile long. You can see the holes in the mountain that they put there to let light in because there's no electricity there, and they dumped the debris that they chipped away from the rocks right out there. You can actually see down here, you can see some of the rubble that they dumped out. That worked out real well for them because shortly after they were done with the road, the Chinese government decided to let tourists in, and this became a pretty hot tourist spot. Everybody wanted to see what these 13 men did. It took them 5 years to do it, and that town's now thriving. Here in the Trollhättan Road in Romsdal County in Norway, this is something that kind of is closer to what we're doing today, but you can see that there's what are called switchbacks there. It makes the road longer but not as steep, and at the end of each switchback is a hairpin turn. You can see this bus is going to have trouble navigating that turn, but nevertheless there's a reason why the engineers build roads that way. This is the Stelvio Pass Road. That's in the Italian Alps, and you can see the switchbacks again here. And you can see these are actually parts of a guardrail. This is right beside the road. The people who are standing here taking the picture actually traveled right up this road right here, and this switchback comes right to here. Gave them a good vantage point to take the picture. Then there's Leisfjorden Road in Norway. Again, you can see the switchbacks. This right here, this is interesting. This is a glacier. And then one of my favorite ones is a pass in the Italian Alps. I mean, look at that. Is that beautiful or what? This one here actually has guardrails. Certainly, they have a little bit more resources to build a safe road than they do in Bolivia. But that brings us to today's task. If we have to build a road to the top of the mountain, how are we going to build it? If we have a volcanic type mountain, we can just go around in circles until we get to the top. That's going to make a really long road that's not so steep. We could do the switchbacks like we saw in the Italian Alps. That's somewhat steep. We could just go straight up the mountain. That's quite steep. Or we could go find a sheer face and find some way to scale it and be ridiculously steep. Those are the options. Now, why do the engineers build the roads like they do? Well, that brings us to the controlling question in the lab. What is the best way to the top of the mountain? The only word in this title that really needs any clarification at all is best. And we're going to define that today as being the least amount of work, where work mathematically is defined as force times distance. So, certainly we're not going to be able to go out today and build roads on mountains. So how are we going to model that in a classroom? We're going to do it with a table. That's going to be the mountaintop, and a wooden plank will be our road. This wooden plank you see oriented right here is not very steep, and that'll represent this road. This wooden plank here is angled a little bit more steeply. That could represent the somewhat steep road. angled a little bit more steeply, could be the very steep road, and if we just put it straight up and down, that could be the ridiculously steep road. So our setup looks something like this. We'll only use one board today, but we can put it at different angles. Angles A, B, C, D, and E. And for plank A, there's the angle, plank B, there's the angle, and so on, with angle E being 90 degrees. On these planks, we should be able to measure the distance the truck has to travel to get up to the top, as well as the force it takes to get it there. Then we'll be able to make calculations. Force times distance gives us work, and then we can plot work versus angle and get ourselves some sort of graph. Certainly it's not going to look like that. So what measurements are you going to have to take today? Well, first off, you're going to have to measure force, and we're going to use a spring scale to measure that. This simply shows the setup. It's not too difficult. The only thing we want to make sure we do is when it does come time to pull this cart up, we're going to want to pull it up the hill at a very slow, very constant speed in order to get a nice measurement. How are we going to measure the angle? Well, the angle right here, we're going to measure that using a protractor. And this is worth a little bit more discussion. How do you use a protractor? Well, first off, we have to know the angle. This right here, the tip of it, that's called the vertex. And the vertex goes in a very special place. A lot of times I'll find students put the angle right like this. And that's not right. The vertex of the angle has to go in a very special place. This little circle right here, that little white dot there, that's where the vertex goes. So this angle is going to sit right in here like this. And you'll notice that this right here is right along the 0 line. This point right down here is 0, here's 10 degrees, and here's 20 degrees. And if we look very carefully, we can see that this angle is 10 degrees, 20 degrees. Looks like it's pretty much 20 degrees right on the button, so we'd write 20.0 because we can read this protractor to the tens place. In the lab, however, this measurement's going to be a little bit more difficult because this plank here has some thickness to it, and that's going to make some things harder. Let me show you what I mean. If we have an angle that's made of something thick, when we go to place it on the vertex, it's hard to figure out exactly where to place it, especially when you see what's going on over in this area. So what are we going to do? Well, if we look carefully, you'll notice that this shape has the same angle as this black shape, which is the same angle as this right in here. And that gives us a way to make this all work out. We can simply take this shape and line up the inside part of the angle with the vertex and still get a measurement. This right here would read 10, 20, 1, 2, 3, 4, probably 24.1 degrees. So, what does that mean back up here? It means we'll use the protractor to measure this angle right in there. And we should be able to get a pretty good measurement. Now, the only way I've seen people struggle in this lab is with the distance measurement. When you have the plank fully extended, then the distance measurement is easy. It's from the point where the back of the car is touching the ground, and then the car has to travel all the way up to the back of the car until the back of the car has reached the height of the table. How far is the car traveling? Well, you just take this mark right from here and that mark right there, and you measure the distance in between, and that's the distance. Here's where people run into trouble. When you angle the board more steeply, the same rule applies. We want to know how far the car has to go from the floor up to the height of the table, right there, and then we just measure the distance in between. And that's the distance. For some reason, every year I run into a little bit of trouble because students, instead of measuring how far the car has to travel to get up to the height of the table, simply measure the length of the board again. Well, the car doesn't even use this whole part of the board up here to get to the top of the mountain, so we don't even need that. We can ignore that and just deal with the part of the board that the car uses to get up to the top of the table. So here we have it. We have roads A, B, C, D, and E, and angles A, B, C, D, and E that are corresponding. And here's the graph that we have to make. In order to make that graph, we're going to need to calculate work. And in order to get our error bars on the graph, we're going to need to work with some uncertainties. Here's a sample calculation for 35 degrees. I made up these numbers. This would be an example. If the force was 150 plus or minus 20 newtons and the distance was 12.2 plus or minus 0.3 meters, our best value uses 150. 12.2 meters gives me 1,830 joules. Here's the max, here's the min. This should look familiar. Feel free to pause the video at this point to look at this more carefully. We look at the spread between the max and the best value. We get 295. The spread between the best value and the minimum, we get 283. Here's our raw number. And if you look at that, we have some uncertainty cropping up here in the hundreds place. So we chop everything else off, leaves us with 1800 plus or minus 300 joules. So in an angle of 35 degrees, the work is 1800 plus or minus 300 joules. So what are you responsible for? Before you come into the lab, you need to view this video until you have a complete understanding of the three types of measurements you must take. Those are the distance up the mountain, the force required to get the car up the mountain, and the angle. You need to know how to do the calculations for work. Finally, have your lab sheet set up. The lab sheet needs a title. You need your name, date, and period in the upper right-hand corner. The controlling question is simply, what is the best way to the top of the mountain? For your procedure, we just need a few lines written, a brief explanation. Your diagram is where you need to take some time. Your diagram needs to show the basic setup. You need to show where you're taking your measurements. And that's angle, distance, and force. Last thing is we need our data section. In your data section, you shouldn't have a blank table. The table should have headings. So you'll have the headings for the table like trial or angle, distance, trial 1, trial 2. These things all need to be filled out. And so you need to do some thinking ahead of time about how you're going to organize that. So when you come into class, you're ready to go. After you've thought through this, you'll also have a lot better idea on what you're going to do in the lab. That should prepare you. Thank you for watching. This has been Mr. Bixel's Tutorials.